Hi, my name is Masood based out of Rankooh, and this is a joint work with my PhD advisor, Dr. Ghulamreza Qasemsani at Sharif University of Technology, Tehran. Many of you are probably familiar with SAT-based classical planning. In SAT-based classical planning, a potential plan is modeled as a sequence of steps between, and we have a sequence of states. We start, the first state is our initial state, and these steps transform steps, one step to another, and the final step is our goal state. And when we want to translate this structure to SAT formula, we have assigned binary variables to each proposition and each action, and we translate actions, the preconditions and effects of actions by clauses, some logical clauses. Then we give the whole structure to the Boolean representation of the structure to SAT solver, and the SAT solver chooses the actions that are in the final plan. We have different kinds of semantics in SAT-based classical planning. There's one-step semantic, which requires each step to have just one action. We have for all step semantics that allows a step to have more than one action, but those actions should not be conflicting. In fact, we require those actions to be executable in any possible order. And there exists step semantics that we should have at least one sequence by which the actions are executable. Well, if we actually want to encode there exists semantics, we need cubic number of clauses, which is not possible. For solving this problem, there's a way we assume that the order of the actions are fixed, and SAT solver chooses from this order. And we also require the action to not be conflicting. An earlier action in this sequence cannot be conflicting with a later action, cannot delete the preconditions and effects of a later action. This way, it can be encoded in linear space. And now I'm describing temporal planning. In temporal planning, we have temporal plans which have two events, the starting event and the ending event. Each event is like a classical action, so they can have preconditions and effects, and as a result, an action can have different preconditions and effects upon starting and ending. An action also can have overall conditions, and each action should have a rational number as its actual duration. And one straightforward way to translate temporal planning into SAT-based approach, a SAT formula, is that we consider the members of each step as events, temporal events, instead of classical actions. So an action can start in step 1 and can be ended in step 2. This way, we need extra proposition to represent that an action has been started but not finished yet. And we also need some time labels associated with our steps for imposing the temporal constraints of the problem. And if action A with duration tau is starting in time t1 and is ending in time t2, the difference between t1 and t2 must equal tau. we have used another approach. The result of, as I said, we have extra propositions defining the agenda of each step. These things that I'm showing with triangles. And as a result of this kind of representation, we require all the events in each step to be executed simultaneously. And this approach has been used in previous SAT-based temporal planners like STEP, TSAT plan, and TMNP-SAT. We use another approach. We abstract out all the temporal constraints of the problem, all the durations and temporal labels, and the result is that the plan that we get from solving this kind of formula is just causally valid, not temporally valid, because we have preserved all the causal constraints of the problem. How can a plan be causally valid but not temporally valid? It's like when you have two actions, one longer than the other, and you want to put the longer actions, to execute the longer action inside the shorter action. It is possible. It is like the thing that Gerard mentioned at the start of this session about that we don't have enough time to do all the tasks. And this causes, when we want to schedule the events of this plan, we use a simple temporal network. But then, in these situations that we have temporal inconsistency, there should be a negative cycle in the STN and in this simple temporal network. So we can find the cause of inconsistency, and the thing we do is that we construct a finite state machine that detects the sequence of objects that has caused this negative cycle. In this example, it is a start of A, then a start of B, then end of B, then end of A. And this sequence, if happens in the plan, it will cause this negative cycle. Then we translate the transitions of this finite state machine into a SAT formula and add the SAT formula to our original SAT formula. So this time that we solve the formula again, the same negative cycle will not happen again. Now, I mentioned that there is different encoding methods in classical planning. In temporal planning, we can have the same thing. Like I mentioned before that we have one step temporal planning, encoding for temporal planning, where we just have one time point in each step. Just one. We can have more than one event, but there is just one time point. We can have for all the semantics for temporal planning. This is possible now that we have abstracted out all the temporal constraints. It is now possible that we can have for all the semantics, and it is so we can have different time points in each of these time points. Different events can happen, but these events, all of these events, should be executable in any order. The events in different time points should be executable in any order. And this previously we have used in an earlier version of ITSAT, and now I'm presenting the new encoding for ITSAT. It is based on there exists a step semantics, and we can have a sequence of time steps in which we can have simultaneous events, but in the current implementation of the semantics, we need each time step to have just one event. But can it make our encoding incomplete? The answer is yes, it can, if we need to have simultaneity in our plan. It can cause problems, but in PDDL 2.1 it is asserted that we cannot require a plan to have simultaneous events, but it can be defined by PDDL 2.1 when an action is producing an overall condition of other action, and the other action are producing an overall condition of the first action. Then the start of these actions should be simultaneous. And if we want our method to be complete, we should be able to detect this situation. And then we detect this, we can go to another approach. We do it by constructing a graph of all events of our problem, the grounded events of our problems, and we put edge to this graph if the nose of this graph is according to or associated with the events of our problem, and if there is a reason of precedence, we call it precedence graph, and if there is a reason of precedence in our actions, we put edges. Like if the start of A is producing something for the overall of B, we put an edge from a start of AS, which is the start of R to BS, and the same edge is put from BS to AS. So we see that we have a cycle here, and this is not just by chance. We see if we don't have a cycle, we can order these events because there is a topological sort of these events, and when we order these events, then the result of the plan cannot need simultaneity. So if we have simultaneity, the cycles must exist in this graph, and the topological sort algorithm is polynomial. So we can check some necessary conditions for this simultaneity prior to start planning. And now I described how we preserve how we implement our encoding. We need, like there exists in classical planning, we need the order of the events to be fixed, and we also need that in this order the starting event of each action be next to the ending event of that action. This doesn't mean that an action should be started and ended in one step, because the SAT planner can choose the starting event in one step and the ending event in another step. As a result, we can have concurrency. We can deal with problems with required concurrency. But if an overall condition of an action is deleted, we should handle this situation. We do that by a message passing mechanism. It is done just by putting variables and clauses into the SAT formula, and we need extra variables. And for passing a message from X to Y, we need a clause if X then Y, and just like this for Y and Z. And this way we send messages. I'm going to explain how these messages are initiated. When first I explain how we preserve the overall conditions. If some proposition P is deleted, we send the message forward to announce that P is deleted. And if some action that requires P as its overall condition receive this message, it knows that it should be started in the same step, and thereby it can prevent being violated by the event that is deleting P. And if this message goes all the way to the next state, and in the next state we see that A is open, is still open, we require A to be opened in this step, not earlier, because if it is a start earlier, its condition, its overall conditions will be violated by negating P. And the same message goes backward. The discussion is very analogous to what I gave, and we also need to preserve that at the start and at end conditions of an action. In classical planning, it's done by sending a message. It's like that. It's not completely like what it is. What is done in classical planning, but they are basically the same thing. We send the message forward, and if an action that needs P, an event that needs P, receives this message, it knows that it cannot be true in the final model. And this is a straightforward generalization to there exists a step encoding of classical planning, but we have done more. When some P is deleted, we send a message forward that means that P is false now. And if now an action receives this message, it knows that it cannot be executed. But if later a proposition P is produced, the message is changed. Now a message is going that P is true, and this time if A is being executed, it's okay. It doesn't have any problem, and P can be deleted and produced as many times as is needed this way. It's an extension to classical there exists a step encoding, and we have implemented this this new there exists encoding into ICAPS, our planner that uses that negative cycle detection, and we have compared it to POP-F, which is an state-of-the-art planner in temporal planning, in expressive temporal planning, and we have used all the domains of the previous IPCs, and in coverage we outperform POP-F in 10 domains. In 6 domains there is a draw, and in 4 domains POP-F outperforms ITSAT. And in a score, I don't want to put emphasis in a score, because if we are performing better in a score, it's the IPC score. It's either by chance or by the fact that we are solving more problems, or slightly by the fact that when you have less steps, because we are optimizing steps, number of steps. If you have less steps, this is unlikely, a little unlikely to have more plans with bigger major spans. And from the point of, for the problems, we solve 53 problems more than POP-F, and the overall score is 32% better. So to conclude this talk, we took a lazy approach. We find a plan, we don't check the consistency of the temporal constraints in each step. We solve the plan, we find the plan, and then we check the consistency. The structure of the problem, when you eliminate all the temporal constraints, the structure of problem becomes very similar to what we have in classical planning. And as a result, you can use those approaches, the good approaches that we have there, and I want to say that SAT-based temporal planning is very promising. This work is in its very early stages, and it's already working very well. I see a big potential to SAT-based temporal planning. Thank you.